Hi, my name is Ivan and I'm a developer relations engineer at Memgrap. Today, I'm going to talk about graph-based stream processing and in general, how graph analytics can be applied on real-time data. So let's dive right in. First, we're going to talk about the graph data model, the theory behind it, and all the basics you need to know to cover this field. So first, what are graphs? Graphs are network structures that consist of nodes and relationships. As you can see on the right picture, there are 3 nodes on this graph. 2 of them have the label person, and 1 of them has 2 labels, city and location. These 2 nodes represent people. They also have properties, key value pairs, that add some additional information to them. For example, this person has the property name and the property date of birth. The city and location node has the property name and the property country. The relationships between the nodes also have a type. For example, this relationship between a person and a city is of the type lives in. The relationship between these 2 people is of the type married to. These relationships can also have properties. For example, wedding date. These properties can be strings, integers, date, time, objects, and so on, just like you will find in relational databases. So, what are graph databases? These are a kind of database that store graphs. As you can see on the left side, this is a typical graph that could also be modeled in a relational database. So what are the key differences? The most important one is that graphs contain the information about the relationships of entities on the entities themselves. So for example, when you have a customer, this customer knows all of its connections to other entities in the network. For example, it's connected to location nodes with the relationship resides at, and it will be much faster to get this relationship and this location in a graph database. In relational databases, when you have to model relationships, you have to use either foreign keys or completely separate tables to model many-to-many relationships. It takes some time, some overhead to find these relationships, and that's where graphs come into play. There are other differences as well. For example, graph databases are usually schemaless, unlike relational ones, where you have strict table definitions. In graphs, a node with the label customer can have one set of properties, while another customer can have a completely different set of properties. If you want to enforce a schema, you have to do it outside of the graph databases. There are some constraints you can enforce, but this is not considered a schema in general. How do you communicate with graph databases? The most widely used query language is the Cypher query language. It has an open specification, which different vendors can follow. It's a declarative language. It consists of clauses such as match, delete, where, very similar to SQL. It has functions, for example, for parsing values, mathematical functions. You can also write custom procedures in different programming languages like Python, C, C++, and Rust. There are a lot of similarities with SQL, but there are also a few differences because the data model behind it is quite different. Here on the left side, we have a typical Cypher query, while on the right side, you can see a SQL query that essentially does the same thing. The Cypher query is a lot shorter because here we don't have to use SQL joins. It becomes much easier to understand the data model and to directly interact with it. It's also much easier to find the relationships between entities because, as I already mentioned, they are part of the entities themselves. So for specific use cases, Cypher is much simpler and easier to work with than SQL. Of course, there are different use cases where Cypher wouldn't be easier, wouldn't be better, and it's better to stick to relational databases or to key value stores or other NoSQL approaches. So where do we use graph analytics? What kind of industries have been applying it in the last few years? So first, what is graph analytics? This is a general term that describes traversals in graphs as well as graph algorithms. Some of the most famous ones are community detection, the PageRank algorithm, shortest path, breadth first search, depth first search, and so on. While graph traversals usually mean going through the graphs, finding relationships, and so on. So with graph analytics, you can find more information about your graph and network. For example, Google has famously implemented a PageRank algorithm to measure the importance of web pages. This is a graph algorithm. Facebook uses community detection on its platform to find interconnected clusters of users, and Amazon makes use of collaborative filtering for product recommendations. There are quite a few companies in today's world that make use of graphs because sometimes it's much easier to model the domain with a graph. Graphs are very often found in social network analysis. Here we can use graph algorithms for link prediction to find nodes that have the potential to have a relationship between them, community detection that finds highly connected clusters of nodes. Supply chain management has been a very recent topic where graphs have also found some use. Here you can do business risk analysis. It's much easier to find a weak link in a graph where there could be potential disruptions in the supply chain, where one node could maybe disrupt the graph, break it in two, and so on. Fraud detection is also a very famous use case for graphs. Here, there are a lot of relationship between, for example, credit cards, POS devices, transactions, and the overhead that's found in relational databases can sometimes make it seem like the analysis takes a lot more time than it should. So graphs can offer performance benefits in this field. Now, let's go to the topic of graph stream processing, now that we know what graphs are in general. So stream processing is a technique where input data is being sent to a stream processing engine, and some kind of graph traversals and graph algorithms are being run in real time on this data. Once the results of the traversals and algorithms come in, the input data could be enriched and stored somewhere else. The results could be visualized. They could be sent to some other output stream for other applications to use on a later time, and so on. So the whole concept revolves around input data that's being generated constantly, a stream processing engine that constantly calculates some kind of insights, tries to find out some information about the data, and then sending it onward to be stored, visualized, or something else. So where does Memgraph come in? Well, Memgraph is the stream processing engine in this pipeline. It's a platform for graph computation on streaming data, and it's powered by an in-memory graph database. So what does that mean? Memgraph stores graph data in memory. It's a graph database, but most of the use cases where Memgraph is used include real-time data sources, and it's very important that the results come in as fast as possible, which means that an in-memory architecture is very beneficial. It's also implemented in C++ to avoid memory problems and to make it as optimized as possible. Memgraph can be used to run graph traversals, graph algorithms. You can even implement your own if you need to in Python, C, C++, and Rust. And you can directly connect to streaming sources such as Apache Kafka, Apache Pulsar, or Red Panda. We are also going to use a Python library called GQLAlchemy. It's an object graph mapper, which means it provides a connection between Python objects such as classes and graph objects. You don't have to parse anything yourself. There is a serializer and deserializer as part of GQLAlchemy. There is also a query builder, which means you don't have to learn the Cypher query language. This write snippet demonstrates it. You can use Python methods and Python classes to construct queries and to interact with graph objects instead of using Cypher. There is also an option of on-disk storage. Because Memgraph is in memory, you can choose to save a part of your graph properties on disk if they are too large and if they are not needed in the graph computations inside of Memgraph. GQLAlchemy also offers graph schema validation. As I already mentioned, graph databases are usually schemaless, but sometimes you want to enforce a strict schema where this feature can come in handy. So now let's talk about stream processing architecture, how a graph application that analyzes streaming data usually looks like. And I'm going to show you a demo application that my colleague and me developed to showcase a few very basic features. The demo application I'm going to show you uses a Twitter data source. We scraped Twitter during the last holiday season. We wanted to find all the tweets with hashtag Christmas, and we wanted to find the most influential users in that network. So we created a CSV file with the scraped data, and the Python script sends every few seconds messages to a Kafka topic. So we use Kafka for all of the communication between the services in our app. Memgraph ingests this data as it's being created and runs some graph algorithms. In this case, the PageRank algorithm and the community detection algorithm. Once the results are calculated, they get sent back to a different Kafka topic. So the backend application can also consume this data, and so the front-end client can visualize it, so we know what's happening. This is the basic outline of the architecture. And aside from Kafka, which is used as the message broker, there is also this connection between the front-end client and the backend server, which is established via WebSocket, because we want to visualize everything in real time as well. As I said, we are working with a Twitter network. The data model is pretty simple. There is only one type of node, which is labeled user. Each user has only one property, which is username. And the relationships between them are of the type retweeted, because we scrape Twitter for tweets and retweets. We wanted to find the most Christmassy person on Twitter, which is why we're searching for all the tweets with the hashtag Christmas. And to find the most influential user, we are using the PageRank algorithm. And to find communities of users, we are using community detection. Noteworthy difference here is that we are not using the traditional PageRank algorithm or community detection. We are using dynamic implementations of these algorithms. This means that the PageRank algorithm is not run on the whole network, because that will take up too much time once we have a lot of nodes in the network. The dynamic algorithm only calculates the PageRank value for the nodes that are affected by the newly created or updated ones. The same goes for community detection. So these dynamic incremental algorithms save on computational time and resources. They are perfect for stream processing. So let's power up the demo application. We used Docker Compose to make everything a bit easier to start and to maintain. Now, almost all of the services are being started. I just have to power up the front-end client as well. The front-end client is a React application, and the visualization is done with the D3JS library. It's an open source library, and I definitely recommend it if you have any needs to visualize networks and graphs. I seem to have encountered a simple bug, as it usually goes with these live demos. Let me start it up again. It will only take a few seconds for all of the services to start, the containers to power up. In the meantime, let's check the front-end client. Okay, so everything, yeah, all of the services except the front-end client have been started and are awaiting. Now let's just wait a few seconds. And the front-end client is up and running as well. The app is listening on localhost 3000. And we should see messages being displayed in a few seconds. And yeah, here they are. So as you can see, the graph is being constructed. New messages are being sent via Kafka, and they are being visualized with v3.js. It may not look like a network now, but in a few seconds, it will definitely fill up a bit. This is the PageRank visualization. As you can see, the radius of the nodes differs. This is because it's directly proportional to their PageRank value. So the larger the node, the larger its influence in the network. The radius also changes from time to time. This is because of the dynamic algorithm that recomputes the PageRank value for the nodes that are affected by the newly created nodes or updates in the network. Down below is the community detection visualization. Here, the nodes have different colors based on the clusters they belong to. So these red nodes, they belong to the same cluster, and they are also changing from time to time because their cluster values are also being recalculated if there are some changes that affect them. The graph is getting a bit larger. As you can see, the largest node has the username World Music Award. This was also the largest Twitter account at the time of scraping, so it makes sense that it's the most influential user in the network as well. You can also use a visual interface to query the database and return the data. I'm going to use Memgraph Lab. This is a pretty simple Cypher query. It finds nodes and their relationships. It returns them. And I'm going to limit the results to 200. As you can see, currently there are 62 nodes and 51 relationships in the network, but this number will keep growing while the demo application is up and running. So now let's execute the Cypher query. So this is the graph, but it's just a bit too plain. So I'm gonna apply a style on it. I'm gonna use this one. This is a language similar to CSS, but it's specifically designed for graphs. And as you can see, this is the largest node in the network, and the username is World Music Award. It belongs to the cluster 3, and this is its PageRank value. Now let's get back to the presentation, so I can cover a few of the things that are happening in the backend and how these results came to be. So this is kind of the pipeline for graph stream processing and how to set it up. First, we have to define a transformation module that will map JSON messages that are sent via Kafka into Cypher queries, so they can be saved to the graph database. So the transformation module tells us how JSON messages are mapped into the graph database. Then we set up the algorithms that are going to be ran on the data in real time. In this example, one of the algorithms is the dynamic PageRank algorithm. So we are creating a trigger that's going to be executed every time there is an insertion or deletion in the graph, because that means that the network structure, the graph structure, is changing. Third, now that we have created a transformation module and we have set up all the triggers, we can start the stream. We can start ingesting from a Kafka topic. And number 4 is consuming the results and sending them again to a different Kafka topic so they can be used in consumed in other services in our application. So the transformation module is pretty simple. the JSON messages that are being sent only have two attributes. So source username and target username. The user that created a tweet and the user that retweeted this tweet. This is the Cypher query that gets executed every time a new message comes in. Merge is a Cypher clause that essentially creates a node or relationship if it doesn't exist. If it exists, it won't be created. So first, we create the first user with the source username. Second, we create a second user with the target username, and then we create a relationship of the type retweeted between these two users. That's more or less it about the transformation module. Now, about setting up the trigger for the PageRank algorithm. I'm using GQLAlchemy, the Python library for connecting to Memgraph and for executing these Cypher queries in Memgraph. So first is the initialization query for the PageRank algorithm, for the online dynamic PageRank algorithm. And then we create a trigger, and it gets executed each time there is a created vertex. Vertex is another name for node, whenever there is a new edge or whenever there is a deletion in vertices or edges. When the PageRank value is calculated for the node, it gets added as a property to that node. So node.rank equals the newly calculated PageRank value. And then we call a custom procedure, which is called publisher.updateRank. This is a very simple Python script that contains a Kafka producer. Each time a node gets a new PageRank value, we need to make sure to send it to a Kafka topic, so the backend server and the front-end client can also visualize this change in the value, because the radius of the nodes depended on the PageRank value. The same goes for the community detection algorithm. We create a trigger, and we again call this publisher.justUpdateCommunity in order to send the updated cluster to a Kafka topic. After we created the transformation module and set up the triggers, we can create and start the streams in Memgraph. So this is a very simple way of creating the stream with GQLAlchemy. We define a name, we define the topic where we are listening to, the transformation script that we created in the first step, which tells us how to map the messages into a graph. And this is the address of the Kafka cluster. In the end, we also need one more trigger, which is going to send all of the information that's created in the graph to a Kafka topic. So each time there is a new node that gets added to the graph, we want to be able to visualize it in the front-end client, which is why we are again sending it with this custom procedure, publisher.create. And in the end, these are the results, the visualizations. The pipeline maybe seems a bit complicated, but once you create your first application or you play around with a demo in a programming language of your choice, you should get a hang of it. As already mentioned, for the visualizations, we use the D3.js JavaScript library. It's a pretty nifty tool, especially for visualizing networks. If you want to play with a data set, the Twitter data set, you can also do that online in your browser without installing anything on Memgraph Playground. We created a very simple sandbox with it where you can run Cypher queries and get to know graph analytics in general. So here again is the very simple data model, and here are a few sample queries which you can run on the graph. This Cypher query calculates the PageRank value for all of the nodes, and it returns all of them in descending order. So as you can see, World Music Award is still the node with the largest rank in the graph. You can also visualize it. Here we only returned the username, but if we return the whole node instead, the graph will get visualized as well. So that was it. Thank you for your attention. And I hope you learned something and you enjoyed the rest of the conference. Bye.